This video continues the addition and subtraction of vectors. We're going to talk about how to approach this mathematically. Now, drawing a picture is good. Let's say we have a vector A, and we can say that vector A, I'm just going to make up some numbers. It has a length of 8, and it points at an angle of 65 degrees. This vector could represent a position vector, a velocity vector, acceleration vector. Ultimately, regardless of what the vector represents, we approach solving problems using them mathematically the same way. So we'll just say this vector length is 8. We're not going to assign a specific meaning to it. And then let's say we have a vector B that points directly to the right, a length of 7. So 7, we could technically just say 0 degrees. That would be the magnitude and direction. So if we want to find A plus B, as we did in the last example, we can draw A, and then where we end A, we draw B. The result, the answer, starts where we started and ends where we just ended. So the result, I'm just going to say this is vector R. Vector R represents A plus B. Now we know vector A has a length of 8. Vector B has a length of 7. R here is not going to have a length of 15, 8 plus 7, and again, that's because of the differing angles. Mathematically, if we think about vector A having an x component to the right and a y component pointing upwards, we can definitely find those components. And then vector B is all x component, no y component. The resulting vector takes into account the rightward vector AX and the rightward vector BX. And ultimately, we can say the x component of this resulting vector is simply the x component of vector A plus the x component of vector B. Similarly, the y component of our final answer is calculated by adding the y component of vector A, that's over here, to the y component of vector B, which in this particular case happens to be 0. This setup in finding the components of our vector answer is applicable regardless of how many vectors we're adding together. So in our original picture, having vector A, then vector B, with our result pointing over here, we could figure out an angle in here, use law of sines, law of cosines, to solve for the length of this side and ultimately what angle it points at. Totally valid. But as soon as we have more than 2 vectors that we're adding together, it ends up being cumbersome to use law of sines, law of cosines, because those require just 2 vectors at a time. They require a triangle and not specifically a right triangle. If we want to say the sine of theta is the opposite side over the hypotenuse, or cosine of theta is the adjacent side over the hypotenuse, or tangent of theta is the opposite side over the adjacent side, we must be working with right triangles. That's where these x and y components come from. When we break a vector down into its x and y components, the x component always meets up with the y component at a right angle. meaning we can totally use sine theta, cosine theta, tangent theta, these definitions. So my approach to a problem like this, let me come back. Typically, I like to just come over to my original vector, just draw out vector A by itself. Make this little triangle. Anytime we're trying to write out our rectangular components, we can always draw a little triangle with our vector as the hypotenuse. So since this triangle has a length of 8 and is in an angle of 65, in this triangle, the x component is adjacent to that side. So I could say the cosine of 65 would be this x side over the hypotenuse, which is 8. That makes the x component 8 cosine 65. Similarly, the y side, if I say the sine of 65 is the opposite side over the hypotenuse, that makes the y side 8 sine 65. So ultimately, we can say vector A is 8 cosine 65 I hat, because it points to the right, plus, because the y component points upwards, 8 sine 65 j hat. So we have vector A in vector notation, meaning in terms of its x and y components. With the vector B I have chosen, it only has an x component. We can simply write it as 7 I hat. As we're starting, you might find it helpful to say 0 j hat. Ultimately, what we're doing, as we showed over to the right here, to find the x component of the answer, the result of adding vector A and B together, we're going to take the x component of vector A, the x component of vector B, and add those together. So our answer's x component is going to be 8 cosine 65 plus 7. I'm going to go ahead and plug that into my calculator. So 10.4. I'm not going to worry about rounding quite yet. The y components we will find by adding the y component of A, the y component of B, which in this case is 0. So 8 times the sine of 65 is the y component of that resulting vector. 7.25. So this, coming back to this picture up here, I'm going to draw it a little bit differently. We're saying that this x component of the answer of adding A and B together is 10.4 to the right and 7.25 up. This vector we drew in the first place to represent R looks like this. And we should not only be able to figure out the x and y components of this, but we should also be able to find the magnitude, so the length of that vector, and the angle it points at. So the magnitude of the vector comes from Pythagorean theorem. And then we know the tangent of that angle would be the opposite side over the adjacent side. So we can take the inverse tangent of that to find the angle. So here I'm getting 35 degrees. That's what this angle in here ends up being. And then the length, plugging in the Pythagorean theorem, the length ends up being 13. So rather than adding 8 and 7 and getting 15, the length of this vector ends up being shorter because vector A and B are not along the same line. We can always maximize a vector if those two vectors are pointing in exactly the same direction. We could minimize it if they point in exactly opposite directions. But ultimately, we're just trying to get to a point where we can look at motion in terms of how velocity and acceleration work together to figure out a final position of an object when there's motion happening both horizontally and vertically. We will also use this concept of vectors to talk about forces, pushes and pulls. Vectors are applicable there as well. Okay, I want to just do one more example really quick. Let's say we have a vector that has a length of 5 at an angle of 50 degrees. And then another vector that has a length of, that looks shorter, so we'll say 4 at an angle of 10 degrees below the negative x-axis if we were to draw a coordinate system there. If this is vector A and this is vector B, I would like to calculate the answer to the question. I'm making it up. So 5b minus 2a. Let's find this resulting vector. So again, we need our vector in terms of its components in order to easily add or subtract. I personally like to draw my triangles representing these individually to the side. I'm going to actually call that, just put the 4 on there. I know vector B points to the left and then downwards. The angle in here is 10 degrees. So this x side, I can call this B sub x. We do know what points to the left. We can put the negative sign on now, or I like to just represent it with the arrow and then put the negative sign on when we write it out as a vector B. So I'll write it out as a negative I hat. But in terms of labeling the side, because that side is adjacent to the angle, this will be 4 cosine of 10 degrees. Walk through that, taking the step, cosine of 10 is adjacent over hypotenuse, if you need to see that. This side over here, the y side, it points down, which I've represented by drawing my arrow downwards. Because that side is opposite, I use 4 sine of 10. Again, you can show that to yourself by saying the sine of 10 degrees is the opposite side over the hypotenuse. So in terms of setting up vector B, to represent this, I would say negative 4 cosine 10 degrees I hat. The negative I hat means the negative x direction. And then minus, because we see this y component points downwards, 4 sine of 10 j hat. Now, typically, I don't put the negative signs on my triangle, though you totally can. There's nothing wrong with that. But you do want to keep in mind, for example, if you take inverse tangent of a negative number, meaning x might have been positive and the y component might have been negative, or vice versa, your calculator cannot distinguish coordinates 1 and 3 and 2 and 4. So you just have to really think through your answer and what you're calculating in order to make sense of your answer. I learned along my educational journey that it was safest for me to just assign the number there, put an arrow representing the direction, and then include the direction when I wrote out the vector in terms of vector notation. So that's how I approach it. Now we also need to write out vector A and figure out its components. We know it points to the right and upwards. This x component side is adjacent to the 50 degrees, so we will calculate the length of that by 5 cosine 50. The y component we will calculate by 5 sine 50 because it's opposite. So we can write out vector A saying, we know it's positive, so I'm going to just write positive so I know I'm accounting for that direction. And then plus 5 sine 50 because it has a positive y direction. All right, so now that we have the components, previous example, we said the x component of the result, the answer, was equal to the x component of vector A plus the x component of vector B. Ultimately, when we look at this question, we can say the x component of the answer, if we multiply 5 by the x component of vector B, because that's what it's telling us, 5 times vector B, that means vector B is going to be 5 times longer, but that also means its components, the x component and y component, will also be 5 times longer. So we can say the x component of our answer is 5 times the x component of vector B minus 2 times the x component of vector A. So it's similar to what we did in the previous example. The previous example, we were just taking vector A plus vector B. And that's why we simply needed the x component plus the x component to get the final x component. To find the y component of this overall vector, we're going to take 5 times the y component of B, and then minus 2 times the y component of A. So let's go ahead and do this. 5, the x component of vector B is negative 4 cosine 10. Negative because it points to the left. In the mathematics of solving the problem, we need the sign in there. So minus 4 cosine 10 is the x component of B. And then minus 2 times the x component of A. So 5 cosine 50. The minus sign flips the direction. So instead of having AX going to the right, it's now going to the left, and it's 2 times longer. So let me just throw in these numbers. Minus 26. So that means this x component points to the left and has a length of 26. For the y component, by is negative 4 sine 10. So we're accounting for it pointing downwards with the negative sign. And the length of it is 4 times the sine of 10. And then minus 2, the y component was 5 sine 50 for A. Plugging these in. I'm getting negative 11. What that means, now technically you can draw out in a picture what we mean by 5b minus 2a. We don't need to. I will always draw out what we mean by these results though, because oftentimes if our problem gives us a vector or vectors in terms of magnitude and direction, it will often ask us to list our answer in terms of a magnitude and direction. And so I just want to take this one step further. Technically, we can say that the resulting vector is negative 26 I hat, so pointing to the left in the negative x direction with a length of 26, negative 11 j hat, pointing downwards with a length of 11. That is a perfectly valid representation of the answer. But had we been asked for the magnitude and direction of this resulting vector, we're not done. So I recommend always drawing what we mean by that result. So to the left by 26 and down, so we start where we ended, down by 11. This is what vector R, the resulting vector, looks like. The x and y components always meet at a right angle, so we can find the magnitude of our Pythagorean theorem comes in handy. So one side squared plus the other side squared. The magnitude of this vector (28). I guess technically we should only have one sig fig since I only gave us one sig fig when making up the question. Theta, this angle. When we say the tangent of this angle is equal to the opposite side over the adjacent, technically they're both negative. And so either way, whether I write them both negative or not, when I take the inverse tangent, my calculator gives me an answer of 23 degrees. That's what this angle is. So in terms of writing my answer, it has a length of 28, but I can't just say it 23 degrees. If you remember, magnitude and direction is based off of the polar coordinate system, where theta is measured counterclockwise from the positive x-axis. So ultimately, it's all the way around. So 180 plus 23, 203 degrees, or approximately 200 degrees in terms of sig figs. This is valid. We could technically say 23 degrees below the negative x-axis. That is descriptive enough to represent what we mean by that 23 degrees. But we do need to be careful in describing our answer. If we just flat out say an angle, then we are implying that is from the positive x-axis measuring counterclockwise. Okay. The approach to problems using vectors, we will approach them using these components, simply because regardless of the number of vectors we're trying to add or subtract, this concept of adding just x components together to get a final x component is always valid. It doesn't matter how many vectors you have. And so ultimately it's the most effective way to get to an answer. So I will do a couple more examples separately so you can watch them separately. And then the last thing we will talk about specifically for the vectors chapter is a tilted axis, which we'll get to.